This is the future of information from the program in Science, Technology, and Society at Stanford University. As we have learned in the first of this two-part series, the system of modern science is not infallible. Biases in research can emerge from financial conflicts of interest, but other biases can emerge from how research itself is published. In the system of modern science and academic evaluation, scientists are judged not only by the research that they publish, but also where their research is published. The pressure to publish pushes scientists to come up with splashy results, of the sort that get them into prestigious journals. But the problem here is that truly groundbreaking findings simply don't occur very often, which means that scientists face pressure to game their studies so that they turn out to look a little more revolutionary. A study in the journal Psychological Medicine examined how biases came into play in research on antidepressants. The authors created a data set containing 105 studies of antidepressants that were registered with the Food and Drug Administration prior to the completion of the clinical trials. The study showed that although half of the studies on antidepressants were considered positive by the FDA and the other half were considered negative, 98% of the positive trials were published, as opposed to only 48% of the negative ones. This highlights the issue of publication bias. That is, favoring the publication of results based on the outcomes that are found. The study also demonstrated that researchers were switching secondary outcomes of their studies with primary ones. This process of selectively reporting positive results in a trial while failing to report those that were negative is considered outcome report bias. Another frequent form of misrepresentation of results was also the use of spin to make negative results appear more positive. Statistically non-significant results were reported as if they were positive, by referring only to the numerical outcomes. Others referred to trends in the data, even though they lacked significance. Only 4 articles reported negative results without spin. But spin is very effective. A randomized controlled trial found that clinicians who read abstracts in which non-significant results for cancer treatments were rewritten with spin were more likely to think that the treatment was beneficial and more interested in reading the full text of the article. But it gets worse. Research becomes amplified by citations in future papers. The more research is discussed, the more it's disseminated both in future work and in practice. Positive studies were cited 3 times more than negative studies. This is citation bias. So in this study, according to the FDA, only half of the research was positive. But almost no one would know that. Even thorough reviews of the literature would find that nearly all the studies were positive because those were the ones that were published. This is one reason why you end up with a large percentage of Americans on antidepressants when good research shows the efficacy of many of these drugs is far less than we really believe. But this problem is not isolated to the United States. In 2004, in the Journal of the American Medical Association, a study reviewed more than 100 trials approved by a scientific ethical committee in Denmark that resulted in 122 publications and more than 3,700 outcomes. But a great deal went unreported, about half of the outcomes on whether the drugs worked, and about 2/3 of the outcomes on whether the drugs caused harm. Positive outcomes were more likely to be reported. More than 60% of trials had at least one primary outcome changed or dropped. But when the researchers surveyed the scientists who conducted the trials and published the results, 89% reported that there were no unpublished outcomes. So something is wrong here. There have even been systematic reviews of the many studies of these types of biases, as we see here in an article published in the journal PLOS ONE. It provides empirical evidence that biases are widespread and cover many domains. A modeling study published in the British medical journal Open in 2014 showed that if a publication bias caused positive findings to be published at 4 times the rate of negative ones for a particular treatment, 90% of large meta-analyses would later conclude that the treatment worked when it actually didn't. So this doesn't mean that we should discount all results from medical trials, but we certainly need to address systemic issues that result in these kinds of unfavorable outcomes. There are things we can do to fix the problem. We can demand that trial results be published, regardless of the findings. We can hold authors to more rigorous standards when they publish, so that the results are accurately and transparently reported, and we should encourage journals to publish negative results as well as positive ones. Some journals are already embracing this sort of research. The journal PLOS One, for example, makes a point of accepting negative studies for publication. And there's an interesting blog post highlighted here. The next problem with academic incentives is the reproducibility crisis in science. So what do we mean when we talk about reproducibility? Reproducibility or replicability of a study happens when researchers take an older study that they want to test and then try to reproduce the results to see if the findings hold up. Testing, validating, retesting, it's all part of a slow and grinding process to arrive at some semblance of scientific truth. But this doesn't happen as often as it should. Scientists face very few incentives to engage in the slog of replication. And even when they attempt to replicate a study, they often find that they can't. Increasingly, this is being called the crisis of irreproducibility. So the journal Nature asked scientists if there was a reproducibility crisis, and the answer, with 52% of respondents saying yes, there was a significant crisis in reproducibility in science. So the stats bear this out. A 2015 study published in the British Journal of Psychiatry looked at 83 highly cited studies that claimed to feature effective psychiatric treatments. Only 16 of these 83 studies had ever been successfully replicated. Another 16 were contradicted by follow-up attempts, and 11 were found to have substantially smaller effects the second time around. Meanwhile, nearly half of the studies had never been subject to replication at all. More recently, a landmark study published in the journal Science demonstrated that only a fraction of recent findings in top psychology journals could be replicated. As for the underlying causes, first, scientists have very few incentives to even try replication. Funding agencies prefer to support projects that find new information instead of just confirming old results. Journals are also reluctant to publish replication studies unless they contradict earlier findings or conclusions that have been published in that journal. The result is to discourage scientists from checking each other's work. The second problem is that many studies can be difficult to replicate. Sometimes the methods are just too opaque. Sometimes the original studies had too few participants to produce a replicable answer. And sometimes studies can simply be poorly designed. Again, this goes back to incentives. When researchers have to publish frequently and chase positive results, there's less time to conduct high-quality studies with well-articulated methods that can help facilitate easy replication. So, how do we address the crisis in reproducibility? Scientists need more incentives to pursue replication in the first place. As we've learned, researchers are encouraged to publish new and positive results, and to allow negative results to end up in their file drawers. This has plagued science with the publication bias. Not all studies that are conducted actually get published in journals, and the ones that do tend to have positive and dramatic conclusions. If institutions started to reward tenure positions or make hires based on the quality of a researcher's body of work instead of quantity, this might encourage more replication and discourage the chasing of positive results. According to Stanford University's John Ioannidis, a greater degree of transparency and data sharing would enable replications. Too often, anyone trying to replicate a study must chase down the original investigators for details about how the experiment was conducted, and that can prove to be pretty difficult. In an article published in the journal PLOS Medicine on how to make more published research true, Ioannidis estimates that about 85% of research resources are wasted. So, to make more published research true, he advocates for practices that have improved credibility and efficacy in specific fields to be transplanted to others, which would benefit them, which includes the adoption of large-scale collaborative research, replication culture, registration, sharing, reproducibility practices, better statistical methods, standardization of definitions and analyses, and more appropriate statistical thresholds. Ioannidis also advocates for the selection of interventions to improve research practices to require rigorous examination and experimental testing whenever feasible. Optimal interventions need to understand and harness the motives of various stakeholders who operate in scientific research and who differ on the extent on which they're interested in promoting publishable, fundable, translatable, or profitable results. So, is science broken? No, science is not broken. For better or worse, it still works. Look no further than novel vaccines to prevent Ebola, the discovery of gravitational waves, or new treatments for stubborn diseases, including immunotherapy, using the body's own immune system to fight cancer. Science is getting better in many ways. You can also see the work of meta-researchers who study and evaluate research, a field that has gained prominence in recent years, who also demonstrate that scientific progress is accelerating. But we need to remember that science is conducted by fallible humans and is still subject to our own biases and flaws. By addressing some of these core problems, removing biases and aligning incentives, we can help to accelerate the potential for science to improve our lives.